Hello everyone, this is the second session of this week. In the last session, we mainly look at a simple linear regression with only one input variable x. However, generally, we have several input variables for one output variables. So, a general linear regression model is y, output variable y is modeled by beta 0 plus beta 1 x1 plus beta 2 x2 and blah 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 plus beta p times xp. In total, p input variables. So here, everything is very similar with a simple linear regression. Here, we want to find out the beta 0 hat and beta 1 hat and beta p hat, then minimize the total RSS. So RSS is the same. The definition of the RSS is the same. So it is given as summation of yi minus yi hat squares. And each sample case, the yi hat is given by beta 0 plus beta 1 xi1. This xi1 is x1, the variable x1 of sample I. Okay. So similarly, xip is the xp of sample I. So for each sample, the predicted value of the yi hat is given by in these equations. Because usually we have the multiple samples, so here if we actually rewrite this equation with some expansion, so it should be y1 is beta 0 plus beta 1 x11 plus blah 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 plus beta p and x 1p, and for the second sample, y2 is equal to beta 0 plus beta 1 x 21 plus blah 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 plus beta p x 2p. In this way, in total we have n samples. So yn is equal to beta 0 plus beta 1 x and 1 plus blah blah plus beta p and x and p. So we can rewrite all of the equations like this. So this kind of in total the n equations with the p input variables. This one can be simply expressed by a matrix form like this. Here, vector y is a vector of the n output sample values, and matrix x is an input matrix with observed input variables. In order to include the interceptor term, this beta 0, here we have the dummy column that we filled with all ones. Then the others are actually the observed values of x11 and x1p, xn1 and xnp. Then vector beta is a vector of p plus 1 length, including beta 0. Then E is the vector of the noise. So we can express that vector y is equal to vector multiplication of matrix x times the vector beta plus the vector of the E. Okay. Here, actually this beta vector then minimize. So here what you want to do is we want to find out the beta hat, vector beta hat, then minimize yi minus y hat, because this is a vector, transpose yi minus y hat. This is actually shows the RSS. This is the definition of the RSS in vector form. Okay. So if we find out such a beta hat by applying some linear algebra techniques, then we can easily find out this beta hat is given by x transpose x inverse. So the inverse of the whole x transpose x times x transpose and y. Okay, so this is the solution of the beta head. So it gave you, the analytical solutions. Then in this case, the estimated vector, output vector of the y hat is given in this way because this is a beta, so beta times x. Then the rest of the analysis is also very similar with that of the simple linear regression. So RSE given by the square root of RSS divided by n minus this p is the number of the variable of x minus 1. Okay, so it is rewritten by like this. Okay. Okay, here also, so if you apply some statistical technique, then you can calculate this SE standard error matrix. Standard error matrix of this beta is given by sigma hat times inverse of x transpose of x. So this one is actually p plus 1 by p plus 1 vector. So this the standard error vector is matrix is a big matrix of p plus 1 by p plus 1. Okay, so then it is symmetric. It becomes a symmetric matrix. So in the middle points are on the diagonal part. On the diagonal elements are standard errors. Standard error of each beta. And off diagonals are actually covariance of these the betas among these betas. So if we want to know the standard error of this beta, we just look at the diagonals. So at this point, this is the variance or the standard error square of beta 0, and the next point is SE square of beta 1, and the last one is standard error square of the beta p. Okay, so then everything is simple. We know the beta j hat from the previous equation, and we also calculate this standard error of the beta j hat for any beta. Then by taking, we can find out 95% of the confidence interval for this beta j. Also, we can apply hypothesis test against beta j is 0 or not using the t-test. In this case, t statistic is calculated by beta j minus, because we are testing against 0, so over standard error. Then here we know that okay, so you may not know, but already statisticians calculate that this one should follow t distribution of which degree of freedom is n minus p minus 1. Okay. Then using this one, so we can actually apply this hypothesis test. Okay, so here is an example. We have 50 data points for y with x1 and x2 and x3. So here intercept is beta 0, and this is beta 1, beta 2, and beta 3. Then we set up a model that y is equal to beta 0 plus beta 1 x1 and beta 2 x2 and beta 3 and x3, and find its coefficient. Then result is like this. Okay. As you see here, x1 and x3, they have the very low p-value as well as this interceptor. That means, so we can be sure that x1 and x3 are related to y. However, p-value of the x2, this is 0.04, which actually roughly means that probability that true x2 is 0 is about 0.0. It's about 4%. This p-value is somewhat on the boundary, right? We don't have that much confidence that x2 is not 0. And if you look at the scatter plot with y and x1 and y and x2 and x3 and y, then you can also see this point. Then here we may have the two different models. One is with x2, the other is without x2. If this x2 is really has no relationship with y. Between these two models, which one is more flexible? Can you think? Definitely, the answer is model 1 is more flexible because this model actually includes this model 2. Then which one will have the smaller RSS or higher R square in the given data set? Since the flexible model is usually expected to fit the given data set better, probably model 1 gonna have the smaller RSS and higher R square. Actually, the analysis results show this point. For the model 1 with x2 has RSS of this amount and R square of this amount, but model 2 without x square, they have the higher R square and lower, higher RSS and lower R square. Okay, so but since I generated this data, I know the truth. So in fact, x2 actually nothing to do with y. So the model 2 is the true model. Then, but in terms of the RSS and R square, why this model 1 looks better? It is because of, please think about it. Anyway, so in this setting, if you are very experienced data science, you may want to choose this model 2. Okay, because this RSS R square are not much different, but the model 2 is simpler. In other words, you may want to discard or remove this x2. This analysis actually leads to the kind of the variable selection. There are some data sets of which P is much larger than N. They are high dimensional data. Typically in genomics, we only have 100 patients, which is N, but each human has more than 20,000 of genes, which is P. In general, variable selection guides to find important variables among many variables. Okay? This is related to the bias and variance trade-off. More variables means more flexibility. More variables can reduce RSS in a training set, but it may overfit it. So that's the problem. Okay, then let's move to the non-linearity in a linear regression. Non-linearity can be considered by introducing high-order terms. Instead of using beta 0 plus beta 1x, we can use beta 0 plus beta 1x plus beta 2 and x square, higher order terms. These new high order terms can be considered as a new variables. Okay? In other words, x square can be considered as new variable x2, or x cubic can be considered as a new variable x3. Then the other stuff is everything is the same. Definitely, as the model includes more and higher terms, it has more variables and it becomes more flexible. Okay. Again, here is bias and variance trade-off. This should be bias and variance trade-off. Okay. This is an example. The black line is fitted. Okay, so these points are observed point, and black line. Okay, it's not black, but it's this line. This line is fitted model using the second order term. Y is beta 0 plus beta 1 x plus beta 1 x square. It shows the somewhat the non-linear curve. Okay. So this data can be well modeled with second order terms, because if you look at the x and x square, they have the very low p values. That means this beta 2 here, beta 2 is not 0. Okay. However, here this blue term, this blue line is modeled with up to 5th order, which means it includes of x to the 5th. This higher model has gonna have less RSS and higher R square, but it is too much wiggly. Here intuitively you can see this model is not a good model. Okay, so up to now we assume that x's are continuous variables. The issue we're going to discuss here is how we can consider categorical x. Categorical x means x has discrete values. Y can be similarly modeled like this, using the multiple x variables. But first x1 can be continuous variable like height. Then we have no problem. However, what happens if x2 is something like gender? Usually gender has the male and female categorical variable with 2 levels. Definitely, some people might say we have more than 2 genders, but let's consider here we only have 2 genders, male and female. But even though we have more than 2 levels, it is also possible. So, for example, X3 is a region. This where this guy is come from, this man or woman comes from the Asia or America or Europe or Africa or any other place. This is another categorical region. In this case, it's a 4 level, but more than 4 levels. Then how can you handle this x2 and x3, such a case? Okay, so generally, these categorical predictors are handled by introducing a dummy indicator variables. For the two-level categorical values, we can encode this data with 1 and 0. For example, if this x variable can be either cat or dog, we can model. Okay, so in this case, let's think about this xi is 1. If we encode xi is equal to 1 if this animal is a cat, or 0 if this animal is a dog. Okay, so in this case, if we model this yi is equal to beta 0 plus beta 1 xi, something plus blah blah blah, then if it's a cat, because xi is 1, it is modeled by beta 0 plus beta 1 and epsilon. But if it's a dog, it is just beta 0. Okay, so here this beta 1 is the effect of cat over dog. Okay, here you can easily see encoded value, this 1 and 0 is not that meaningful. Even though you encode this cat and dog with different values. For example, cat is let's say 100, and the dog is minus 200 with some random values. Actually, it doesn't make any fundamental difference, because anyway, the difference gonna be observed by this the beta 0. Okay, there's no fundamental difference. You can easily see this. Okay, so how about the more than two categories? in short, we need to introduce more dummy variables. Let's consider the variable can be cat, okay, here, cat, dog, or horse. Okay? Here, we introduce a dummy variable for cat and another dummy variable for dog. So, this is for cat, so it is 1 or if it's a cat, and 0 if it's not a cat. And x2 is 1 if it's a dog, or 0 if it's not a dog. So then we can set up like this linear equation. So if this animal is a cat, the equation becomes beta 0 plus beta 1 plus error. And if it's a dog, it is given by beta 0 plus beta 2 plus error. If it's a horse, just beta 0. Here beta 0, so this horse is the baseline, and beta 1 is the effect of a cat over this baseline horse, and beta 2 is the effect of a dog over this the baseline horse. The point is that a categorical variable with k categorical values require k minus 1 dummy variables. So even though the one single categorical variable can make a model very flexible, because it is really depends on the number of categories. Okay. Okay, so here is a summary. Linear regression is a simple and interpretable method for regression problems. The confidence interval, the confidence of coefficients can be estimated in a statistical way. Also, a linear regression model can capture non-linear relation within the higher order terms, and categorical predictors are modeled by additive effect. Okay, so here are some references you may want to see more. And okay, so this is everything about this this week, and in the next we will see some practical examples with R programming. Okay, so thank you very much.